Hey Farhan,
Hi Akshay, how are you?
good. I guess it's just we two today.
Sorry.
I guess
Oh
it's
yes,
just we two of us.
yes. I'm also wondering.
That's a lot.
Good morning, everyone. I think we will have to wait for a little while. We have 8 participants right now, and I'm seeing the participant count going up. So probably a few more minutes. Okay, I'll do one thing. I'm going to share the link for today's notebook. So the link to the notebook, which is more or less similar to the notebook we are working with in the office hour on Monday, but it has a few bits of additional code, and there is a small bug fix as well that Akshay has pointed out. So the link is in the chat. Please grab it quickly, and, then we'll proceed. And if you have the link open, then I think we were through steps 1 through 11, so we just need to execute those cells. I'm doing that. As you load the notebook in Colab, you can also do that. So execute everything up to step 11. Sure. So here goes the link again, and I think I'll also paste it in Slack. W3 session. Right. So please load the notebook and run everything up to step 11. Okay, so I hope everyone has registered 12, which was what we were attempting on Monday. And some of us may already have attempted this, may already have found the solution. But the idea was that instead of taking random actions, because we want to collect information about the environment, why don't we refer to the table? Because the table sort of tells us which are the best actions to take in any state. So we shouldn't be wandering around doing random actions, right? And that is what we wanted to do here in step 12, right? And we're calling it greedy episode because again we are using the same greedy approach. Just start in the reset state, then keep stepping through the environment, keep collecting the state, action, and rewards, and keep adding them to a list we are calling episode, right? That was the idea. uh, the code is going to look like, because we already attempted this on Monday, so and it's not very different from what we did earlier with random episodes. So just copy paste, do a quick walkthrough, right? So this is how it's going to look like. You define the list episode, you reset the environment, and you set this flag to false, and then you keep looping. The only thing that has changed, so the table gives you the optimal information at the end, right? So this is so the you use the table to guide your exploration, and then based on your exploration you find a few bits of new information and you use that information to update the table again, right? So unless you are using the dynamic programming based approach that we used last week, and we can't use that now because we are trying not to look at the private APIs. We are trying not to peek into what is behind the environment, right? So in this approach, you will start with a table which is initialized to zeros or random numbers, and then you will consult the table and you will generate an episode. Obviously this episode will have a poor quality. The decisions won't be good enough because it's all initialized to zeros. But then once you have collected that episode, you have a little bit of extra information about which state transitions are present and what is the accompanying reward, and you use that information to update the table. That improves the quality of the information that is in the table. Then you again refer to the table and generate a new episode. That is the whole idea behind this this function that we are calling collect greedy episode from returns table. So we have done this earlier as well, because we were trying to just print the policies, we used to grab the best action corresponding to every state. So this is exactly the same code. We are just getting the greedy action, so we know which state we are in. We just call this idx max method, which gives you the index of the maximum value, and that is what we want, because we want the index or the column that contains the highest return for every row or for every state. That is what this line is doing. And then you feed that greedy action into the step function, right? So you're trying to take the best action, whatever the table tells you at the moment is the best action. You feed that action into the step function, and that gives you the next state. And the rest of the code is similar to exactly the same that we had for the random case. So you just append it, then you set this variable state to next state. And if you run this code, if I run it once, if I run it twice, no matter how many times you run this is going to be uh, the same episode, right? Because at the moment we are not making any updates, so it is referring to the same table. So you're going to look at the same episode, unlike the previous case where if you went up and right, if you ran this, if you ran this cell, then this time it's an episode of length 4. If you run it again, you get an entirely different episode because it was random. But at the moment, with this approach, with the greedy approach, we are getting the same episode back again and again. But of course, this won't happen when you update the table. When you use this information that we just collected in terms of this episode over here, then of course the table will get updated, and the next time you take greedy actions, it's going to look a little different, right? So that is what we want to do in step 13, and it's pretty similar to what we did earlier because the whole idea is same. You have two tables. There's a returns table and there is a visit count table. So the return table just keeps accumulating returns because every time you construct an episode, there will be many instances of state action pairs. So you just record them, you accumulate them. Every time you hit the same state action pair again, you accumulate that value in this table. And finally, in the next cell, you divide it by the visit count. That gives you the average return, right? So the idea is same. Yeah. Is there a question?
Yes, there's one question regarding the maximum episode length. So the max episode length is set to 20. So is there any reason? I mean, it needs to be like, so the basic thing is like how much amount of percentage we want to do the exploration and how much percentage of
Right.
time we want to do exploitation. That's
Right.
uh,
20
so,
is,
like, is there any kind of good number, kind of like 30%, 20% or anything?
so I think the least you could do is set it to something which allows you to reach the goal state. We know that is exactly 20 steps. Sorry, that is not 20 steps. The number of states, state action pair is 20. I think it was just set by me to an arbitrary value. Like any other hyperparameter, you would like to uh, experiment with different values and set it to something more sensible. But 20 seems to be working in this case. We will come back to that question when we are dealing with something more realistic. But for this problem, 20 is fine. You can even perhaps reduce it a little bit, and that will speed up some of the code that we are going to look at later. So right now we don't have a formula, or we don't even have a rule of thumb to pick an appropriate number of steps, but you just want to cap it to something which is sensible, so which isn't too long, and at the same time you want to ensure that if path is feasible, then it's not cut short because the episode length is very low. Does that answer the question?
Yeah, yeah. Thanks.
Sure. So let us attempt to write this code over here. Like I said, it's going to look like what we did with step 11, right? Over here, going to resemble this code pretty closely. But this time we will call, when you are generating episodes, make sure you call the greedy episode generator. We don't want random episodes.
What URL for the notebook should we use?
Okay, so 1 second. I shared this in the chat and in Slack too. But this is basically, so I think the easiest way to grab the notebook for any week is if you go to the base URL, which is github.com/nochowhq/rlinaction, and there you will see all the folders for different weeks and different sessions. But you can also, like I just shared it in the chat as well. And when you load the notebook, you should just run step 1 through 11 because that is already done in the previous week. All right, so we'll go back to implementing this, and we will experiment a little bit with this approach. So I'll start breakout rooms. I'll give everyone around 10 minutes. Like I said, the code is going to look a lot like what we did last time with with our random approach, random steps, random episodes. So it shouldn't be a lot of effort.
You're muted.
Okay, so the breakout rooms are closing in about 10 seconds. And then we'll talk about the code and why we adopted this approach. Okay, seems like everyone is back. So this is the code. Again, I copy pasted it because I had the solution handy and I didn't want to introduce any bugs. Uh, there was actually a bug in our class, very subtle one, which Akshay had caught. So there was an unnecessary uh, statement that was sitting inside a for loop. I have fixed that in this cell. I'll probably show it towards the end of the session. Uh, but if you try to write the code, and here is my attempt, so it looks very similar. This part, the lower four lines, they look exactly the same as they were in the last case, right? What has changed is that we are collecting greedy episodes, and because greedy episodes, for creating those episodes, you need to look at the current state of the table. There is an additional step where we are sort of computing the current snapshot of the table, right? So just carrying out this division right here, uh, and storing that in estimated returns. This is essential that you normalize it by the visit count, so you have an average value or average values, and then use that in the second step to collect greedy episode. The rest of the code is exactly the same as it was in step 11. So if I run this, and it does take a while because it's a little slower, and yep, uh, I'm sure a few of you have noticed this pattern that only some of the rows actually, it looks like only the first row and one entry in the second row, they are getting updated. Why is that so? Well, that's because we are referring to the table to generate new episodes, but the table initially doesn't have any useful information. So if you look at the first episode, this one over here, it was telling us that we need to go south in state 0, uh, going down, and then in you will end up in state 4, but there it was telling us to come back to north, right? Which is just introducing an endless loop, and that is what you can see in the rest of the episode. It is going south north between states 0 and 4, right? This is obviously, this is worse than the random episode, which was actually at least letting us sometimes break out of that zone and be able to explore states and actions which were farther away from the starting state and action. But why did we give it a try? On its own, it's pretty useless. It's worse than the approach that we adopted earlier. You can try to print the policy. It doesn't make any sense. Things are pointing in random directions. Even the table is not updated properly. But what we want to actually do is, and this has been discussed earlier, is that we want to combine the two approaches, right? So the first one, we call it exploration, because when you are taking random actions, then you're just trying to find out what the environment looks like, how does it reward you for different actions, what are the different states, what are the transitions. So that is the exploration part, right? The second thing, when you're looking at the current snapshot of the returns table, that is exploitation, because there is some information that is sitting there in that table. That information is important because that over time the table is telling you which are the best actions to take in every state. So why don't we introduce a little bit of that information when we are generating episodes, right? So we have taken those two approaches separately, but what we really want to do in step 14 is just combine them, combine both the approaches, right? And this is what is called the epsilon-greedy episode generation, right? So there was the random generation, and then there was greedy, approach that we just saw, and this is a combination of the two. And the idea is really very simple. So we are still going to refer to the table. We are still going to take the best action, but instead of being just picking the best action, we are going to introduce a little bit of noise. So instead of picking up the best action every time, we will pick the best action most of the times, but occasionally we will just take a random action, right? And this is exactly what a combination of exploration and exploitation will look like. Okay, so uh, how do we do that in terms of code? Well, you have an array of actions, right? You can get that from the pandas data frame. uh, what you need to do is build up a list like this, right? So whenever you are in a state, for every action, build a list like this one. uh, how is it constructed? So if you look over here, what is happening is, there are, of course, there are 4 actions for every state, but in this case, suppose west is the best action, right? So we want to assign a high probability to west, right? And that is what we do over here. So we assign it a probability of 0.85, and all the other states, they get an equal small share of the remaining probability. So the remaining 0.15 probability is spread over the rest of the states. So everything else gets 0.05, 0.05, 0.05, right? And in terms of, you can do the mathematics. This, if you look at it, then obviously, if you are assigning epsilon to the rest of the states, then, so if epsilon is a small value that you want to assign to the actions which are the non-optimal actions, right? So epsilon could be like zero point 0.1 or 0.05. So you assign epsilon, epsilon, epsilon to everything else, and to the state which is to the action which is actually optimal, you assign it 1 minus epsilon plus uh, you know the remaining value, uh, which we need to figure out the exact formula a little bit, what it will look like. So once you have assigned epsilon to n minus 1 states, how much of the probability is remaining? That will be 1 minus epsilon plus something. We need to figure that out. But if you introduce that, then you have a list of probabilities, you have a list of actions, and then you need to sample from those actions using these probabilities. And Numpy already lets you do that. So there is an API called numpy.random.choice, which takes an array from which it can pick a value, and it takes another array which is the probabilities, and then every time you sample from it, it will give you a different value perhaps, but the likelihood of getting a value with a higher probability will be higher, right? So things get picked up in proportion to their probability. That is what we want to implement here in step 14, right? So again, a lot of the code is going to look like the previous two implementations, but this time we will have to, every time you are in a state and you want to pick an action, you have to construct uh, a list like this one, right? And we are already passing a default value of epsilon of zero point 0.1, so you can use this value. Make sure that the highest, the state with optimal the action with the optimal action, sorry, the optimal action that gets the larger chunk of probability, and the non-optimal ones each get this epsilon by something. So let's try to implement this, and hopefully this will work out better than the previous approach. So we'll go back to the breakout rooms. Okay, I think we're all back. So what we essentially had to do is, and I'll keep copy pasting code and explaining it, but really the only thing that changes here is sort of these two lines. So you can, because we already have the actions, you can access them through the returns table. So that is what we're doing here. But then we're just constructing an array, and it could be a list as well instead of an array. But what we're doing is we construct an array and we just fill it by epsilon by the uh, the denominator, which is going to be 4 in this case because it is the number of actions, right? So if you go back and look at the markdown here, every state gets this epsilon by 4, including the optimal ones. So the non-optimal ones, they get epsilon by 4, epsilon by 4 each, but the optimal one also has an epsilon by 4. It also gets an additional 1 minus epsilon. And if you just sum it up, but it will sum up to 1, which any, like, because probability should sum up to 1, so which makes sense. So
Wouldn't you want epsilon over 3 for each of the other probabilities, and then 1 minus epsilon for the most likely one, if you want 1 minus epsilon for the most likely and equal for the rest that add up to epsilon?
you're saying epsilon by 3 here and then 1 minus epsilon here, right? For the
Yeah,
optimal
right.
one.
Because that would mean a total probability of epsilon for the other states and 1 minus epsilon for the
Yeah, I think that
greedy.
should also work. Yeah, that could be another approach. Uh, yes, if it's epsilon by 3 or epsilon by, okay, yeah. So an alternative could be having action minus 1 here, and then when you're assigning the optimal state, then just add 1 minus epsilon. That adds up to, it should add up to 1 minus epsilon. Yeah, yeah. I think you can use either approach as long as each of the non-optimal state it is getting the same probability. One difference though, I think, if you are using the real difference is if you think about what happens if you set epsilon to 1 in this definition. So if epsilon is 1, then everything according to this definition is 0.25, right? Which means we are assigning equal probability to all the 4 states. But if we use the alternative method where it's epsilon by 3 and 1 minus epsilon, then you have to think of another way. You have to manually sort of set the values, because that will be one special case where we want to assign equal probabilities to everything. So then you have to think of how to do that in that case, and it will make sense in a little bit when we reach that step. But using this approach, it is a lot easier. If you want to assign equal probability, if you go back to the totally random case that we were doing earlier, that is very easy because you just set epsilon to 1, and then everything becomes epsilon by 4 in this case.
Yeah, I
Yeah,
mean, in mine, you would be setting 1 minus epsilon to 1 over the number of actions to get what you wanted.
right. Yep. So then, of course, you need to find out which action is the best one. Again, the same. You can use the same API that we were using earlier, or you can use np.argmax. Uh, this will just give you the argument, the index of the highest value. Why are we doing this? Because we want to find out which action for this state is the best action, which action corresponds to the highest return. So you get that in the greedy action index variable, and then you just selectively update the action probability. This array that we just constructed and filled with epsilon by 4, we are going to add 1 minus epsilon, an additional value of 1 minus epsilon to that. Right. This is basically the difference between this implementation and a purely and the implementation that we did in step 11, where it was purely randomized. And then what we're going to do, of course, because we have an array of probabilities and we have an array of values from which to sample, we use this API and p.random.choice. This is the array from which it will sample. This is the array which are the probabilities. So we do this, and this what will happen is that now it will sample from those 4 actions, but every time you ask it to sample, it will sample in proportion to the probabilities. So because the best action has the highest probability, most of the time you will get the best action for for any state. But sometimes, occasionally, because this is random and other things also have non-zero probabilities, sometimes you will also get random actions out of this. The next 3 states I'm just going to copy paste. This should go here, and this line, because the comment is below, so I'll just move it down. It should be here. uh, hope this makes sense to everyone. This nothing very complex going on here, just whatever we saw in the markdown here, we are implementing exactly this strategy here in terms of the probabilities, and then you just sample from the same array but now using probabilities. So this is pretty much like step 11, but in step 11 we are calling random choice, but we weren't passing this second optional parameter, which is the list of probabilities. And this time we are, and we are calculating those probabilities over here. And this like finishes our implementation. Uh, you should just run your implementation a few times to see that you're indeed getting different episodes, right? So they seem to be all different. This seems to be working, right? And at the moment epsilon is set to 1, so this is fully randomized version, but you can set it to 0.1 and test again, right? So if you look at this one, this looks a lot like what we had previously, like where we started with 0 and then south, then 4 and north. So it again gets caught in that loop for a little bit, but then eventually at some point it takes a random action, because epsilon is small, 0.1, and this 0.1 gets distributed as 0.05 for every non-optimal state. So it takes a while, but it is able to break out of that chain, right? And you can try setting different values to see what is going to work and what's not going to work, right? So in most of the cases we still get stuck, but sometimes we do get out of that loop, right? Okay, so now all we need to do is just apply this approach. The rest of the code is the same. There's nothing to do in step 15 really, but we just want to test out this new strategy. So everything here remains the same. Of course, this function call has changed because now we are using the greedy episode generation. So I'll execute this cell. Yep. So it took a little while, probably a few seconds. Right. And it seems like more cells are getting filled than were when we were using this greedy approach, but the table still doesn't seem to be fully populated. And that sort of makes sense because we set this parameter. If you right, so if you look at this thing over here, right, so we are just passing it the estimated returns. We are not passing it the value of epsilon, which means the default value of 0.1 is being used. Sorry, the default value of 0.1 is being used, and we saw that with 0.1 it still gets stuck in that loop a lot, right? So we probably need to start with a larger value. uh, you can try that. Instead of having 0.1, let's say, let's make it 0.3. I didn't give it a name. Sorry. So there are two optional parameters. There is episode length and there is epsilon. So right, and when you increase this value, when you make it 0.3, then you can see that now more cells are getting filled, and you can also view the policy, try to print the policy, right? uh, it looks like it's still not doing a good enough job because the arrows are still pointing in random directions. Now you can change that by increasing the number of episodes over here. That is something that we need to experiment with. But right now, with this value set to 1000 and epsilon set to 0.3, although the table is getting updated, we aren't yet there. So the policy still looks pretty haphazard. And that is something that we are going to try to fix in the next step. So this intuitively makes sense. We don't want to take either of the approaches where you are purely random or whether you are purely looking at the table. We combine these two. But what we really discussed last time was that this will work best when you start out purely random and then gradually move to a strategy where you're just looking up the table. You are not random anymore, or the probabilities that you assign to non-optimal actions that are really small, right? That is what we are going to do in step 16. So we are introducing this concept of decaying epsilon. There is, it's not a very radical idea. uh, Instead of having a fixed value of epsilon like 0.1 or whatever, start with an epsilon value of 1. Why 1? Because if the breakup that we had earlier, so if you substitute 1 there, you get equal probabilities, right? And equal probabilities, that corresponds to the case where you're picking up actions equally randomly. That is what we did in step 11. We were not using a probability array at that time, but if you don't pass that parameter, then of course the API will assume that everything is equally likely, everyone has the equal probability, and samples based on that assumption. So start out equally random by setting epsilon to 1, but then keep decreasing the value of epsilon, right? And that could be done every episode, that could be done every few episodes. That is something we can experiment with, but this is the idea. So the number of episodes is same like the last time. We start with an epsilon value of 1. We want to keep reducing epsilon to zero point 0.1, but we won't totally stop doing this because there at any point there could be states which haven't been explored. So we want a little bit of randomness, little bit of leftover exploration. So it is still set to zero point 0.1, and we saw that zero point 0.1 there isn't like going to be a lot of randomness. So this is the idea. This multiplier over here will just make sure that every time the new value of epsilon is the previous value multiplied by this multiplier. So it gets a little bit smaller because we are decaying it every episode. So it just needs to go down by a little bit, but you have to make sure that it doesn't go down below zero point 0.1. So this is the strategy that we want to implement here in step 16. So let's go back to the breakout rooms and try to implement this. Again, it's going to look a lot like the previous implementation. The only thing that changes is the value of epsilon will not be static. It won't be a constant. It will decay every time. So let's give this thing a try. Okay. So it wasn't all that different from the previous version. Really, the only change that we need to make is this line over here. So again, I have copy pasted code from my solution, but there are two changes. One is this line over here, line number 14, which is just making sure that we are not going below the minimum value that we set for epsilon, which is zero point 0.1. And then this line number 16, which is ensuring that we are decaying epsilon by a small fraction every time, which is 0.999. And when we are calling this uh, collect episode greedy, collect epsilon greedy episode, we are ensuring that we set the epsilon to the decayed value. And let's test this out. So this is the fourth policy sort of that we have generated so far. Now look at this policy, and I think everyone will have to look at the numbers in the table and see if they are sensible, if they make sense, if they are similar to what we got with dynamic programming. But if you just look at the printed out policy, it looks a lot saner now, right? It is still not providing you a solution, because if you start out here, then you just get stuck over here in this loop. But if you look at some of the other starting states, for example, this one over here, then you are getting a good solution. It is telling you the shortest route. This one over here also has a solution. So has this one, bottom left. So it seems like, the correct solution, we are closer to the correct solution. Maybe if we increase this to something like 5,000, 2,000, something like that number of episodes, we will be able to get there. So perhaps we will be able to get the correct policy. And you have to remember that because now we have introduced sampling, if you run it again, there is no guarantee that you will get the same policy. And you can take a snapshot of this thing and then run this code again, and very likely that you will get to see a different policy, which could be a little different or a lot different. That depends on the different parameters. But we are now, what we're looking at looks like uh, we are very close to an optimal policy. So one approach could be just to go back and perhaps set it to something like 3,000. Let's just try and see what happens if we set it to 3,000, which means it will take thrice the time. uh, which means it will take around 20 seconds or so. And hopefully give us better results.
Farad, could we also introduce one more hyperparameter, like run it in a random fashion up until maybe 1,000 iterations, and then try to use the returns table?
Right, we can do that. So just introduce another for loop over here, and then just have a list of number of episodes. Instead of 3,000, have 100, 500, 1,000, 10,000, and then print the table. And that is something that we will need to do, because I have gone through this solution, I've tried to debug it, so you don't see a lot of that extra debugging code that was used to come up with the solution. But that is ideally what we should be doing, and we will be doing that when we encounter new problems, like when we are doing the project, or when we are attempting this but with a different environment. So you would need to do that, because there's something I'm going to talk about before, in the next step. And you will only realize that, understand that, when you are doing it manually, when you're trying things out. When I ran it with 3,000 steps, let's just try to see what happens, right? So again, I think it has actually deteriorated. The policy that we got earlier, that looked a lot better, this time seems to go haywire. uh, there could be a lot of reasons. This has to be debugged, instead of to find out the real reason why this is happening. This could just be because of randomness. We can perhaps give it another try, just to see what happens when you run it again. Okay. Have things really improved? I don't think so. Uh, yes, we are able to again reach from some of the states, reach the goal state, but
So it
we are
seems
nowhere close.
in most of the cases you're stuck at the beginning. I mean,
Stuck in the beginning. In what sense?
if you look at that policy, the print that you made, I mean, this,
Right, right, of course, right. So if you're so of course the goal is to start from here and then reach the goal state, which is not going to happen with this policy. We'll just get stuck right here in this room. But we can at this table and we can immediately tell that it is better than the previous two attempts, because there are other states there which are closer to the goal state, and from there it seems it's able to learn. So it just seems like somehow this information is not spreading out far enough in the table, and we tried using more number of episodes. That doesn't seem to help a lot. uh, Now this is something that has to either, like, you look up why this is happening and you already know the historical background, or you need to experiment with this code and print what we were just mentioning, that have different number of episodes, start with 100, 500, 3000, and actually print out the table during those iterations at the end of the iterations, and then compare them and then see what is going on, because you are decaying epsilon. So what is the effect of that decay? uh, does that have some impact? Is there a certain number of episodes where things just stop to improve? So if that is so, we can perhaps add a condition for early stopping. We don't need to maybe the table stops to update by the end of 500 steps. So whether you do 1000 or 3000 doesn't really matter, and we can check that with something a similar approach to what we did earlier, right, where we were looking at how much the table is changing between two steps, and then if that delta was small, we were just bailing out. So that has to be done, and you need to manually inspect and manually debug things to see what is happening. But what you will find out if you look at it closely is that the issue really stems from here. Let's see. Yep. So the issue really stems from this thing, right? So what is happening is you are dividing the return. Of course, that is what we need to do, because we need to find the average. So we need to divide by the visit count. Now, if you look at it, and this is something we discussed 2 sessions back, is that as the visit count variable goes up, it has a non-linear effect on the estimated returns, right? So try dividing something by 3, by 5, and you will see that it will just drop down very quickly. Uh, so what is happening is that in the beginning, when we are taking random actions, then visit count happens to be low, and things are updating. You can try plotting the returns. You can see how much they change, and you will see this pattern that in the beginning things are changing a lot, but after you reach a certain number of visit count, the 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 changes that you see in every cell every time you update the table, they get smaller and smaller. And this is squarely the reason why this is happening, because visit count has this non-linear impact being in the denominator. And the way that is usually fixed is what sort of is being done in step 17. So look at our update step right over here, right? So what we're doing is we are updating location s comma a, which corresponds to the state and the action, and we are adding this return value. So return comes from the discounted return for that state in action. But if you start thinking about this, how are these two values different? So what you have here at location S and A, that is, if you divide that by the visit count, that is your current estimate of what the return should be, right? For that state, what is the maximum return based on all the previous knowledge that we have. If you look at this value return, this is again estimate of the same thing, but this comes from your most recent interaction from the environment. This comes from a single episode, right? So if you think in terms of meaning, they are both the same things. One is based on the entire historical data, and the other one is based on your most recent exploration or most recent encounter, most recent experiment uh, with the environment, right? So what we are trying to do is we are trying to accumulate this most recent experience into the experience that we already have. And instead of doing that by dividing the returns, the accumulated returns by visit count, we can take an approach that is very much like what you do in deep learning. So the idea is that instead of having this kind of an update, right, where you just add the return, and because you're accumulating things, then you need to divide by uh, over here you need to divide by the visit count. Instead of doing that, take the difference of this value, the previous estimate, sorry, the value on the left, which is your previous estimate, and the value on the right, which is your most recent estimate. Take their differences. Now that difference tells you how good or bad your previous estimate was with respect to the new estimate, or you can say how different your newest estimate is uh, with respect to your previous estimate, right? So that delta tells you how much that difference is. And then what you could do is something very similar to what we did when we were trying to learn to drive around that track. Just use that delta, multiply that by some small number, which is sort of a learning rate for this algorithm. Multiply it by that small number, and then just add it to your table. Like change the table, change the return, change the entry by that small amount, right? That is the whole idea of something that is called constant alpha. And what this will mean is that if alpha is small enough, then you generally don't need to normalize this by visit count. So you will see that whatever values you get in estimated returns table, they tend to be small and sensible. They won't become too big. They won't blow up over time. So that is what we want to do over here in step 17. Right, we just define another hyperparameter, which is you can call it the learning rate for this algorithm, and the idea is described over here, but I also described it using the code that we saw in the previous cell. You have to take the difference of the current estimate and the most recent estimate, and then multiply that difference by this value alpha, and then just use that to adjust the current estimate, because in the end you have to update the value in the table. So that is how we will do it when we are using constant alpha. Okay, this is sort of the last incremental improvement that we are going to make in today's session. So let us give it some time. This this should probably bring us one step closer to getting convergence, getting a good policy in a few thousand steps.
So this technique is called the on-policy learning or off-policy?
Yeah, we will discuss that. So, but you can start thinking of it, because uh, if you look at how and where you are sampling, and when and where you are updating things, right? So are we sampling from a policy, creating an episode, and then are we updating the policy as we go? Or is it like we use the policy to generate episodes, and then we later on we update the policy?
Okay. Okay.
And
Sure.
we will discuss that in the coming sessions.
Okay,
That is one distinction.
if the issue is just If the issue is just that the geometric sum is it's nonlinear in the parameter, why not just scale it by like 1 minus lambda to the n over 1 minus lambda? Like, why not just compute that geometric sum?
Yep. So you're saying that over here is instead of just dividing by the visit count, you want to scale it up by 1 minus lambda to the power n.
Yeah, in other words, the issue is, right, that you said it's nonlinear because that discounted returns
Right.
is nonlinear in gamma, but we know the formula, right? It's deterministic. It's just a geometric sum. So
Correct.
wouldn't it just be, right, the 1 minus lambda to the n over 1 minus lambda, or sorry, 1 minus gamma to the n over 1 minus gamma?
Okay, 1 minus gamma over, which is basically 1 minus 1 over gamma, right?
Well, 1 over 1 minus gamma, yeah. If you had an infinite, right? But you have visit counts, right? So visit counts
Okay.
is kind of your n, right? It
Right.
would be like 1 minus gamma to the visit counts over 1 minus gamma, or something like that, right? You just have a finite sum.
Right. So anything, if you are able to offset that nonlinear effect, then I think that should work. So we can try that. So let's actually try that approach as well. If you want to stick to constant alpha, then this is the approach, like totally do away with visit counts. But you can alternatively try this other approach. So if you want to multiply it 1 over, and I have to think a little bit about it, but if you're saying if you multiply it by 1 over 1 minus gamma to the power n, that should offset the effect of visit count, right?
Yeah, I mean, I'd have to look up the formula, but I think it's something like 1 minus gamma to the n over 1 minus gamma.
You're talking about the sum of the geometric
Am I
equals,
audible?
right? Yes.
Cool. I tried something a little bit different.
Mhm.
And let me fix my volume because I'm hearing talk back as well. Okay. So I just set the reward on getting success to 50, and that completely fixed my answer. And so I'm wondering if there was an incentive for the
So you're saying
schedule to, I'm sorry, for the picker to just say, hey, let's avoid the end, because I was seeing pretty clear results where all of my arrows were pointing back toward the start, and it seemed like just fixing the goal, fixing the reward for the goal did it.
Okay, that seems to be working. So you just change the reward structure to such that the goal, when you reach the goal, you get plus 50, right?
That's exactly right, and I get perfect answer.
Okay, so that is something that we need to experiment with, the right reward structure, how much you want to penalize or how much you want to reward when you reach the goal state. That is also something that we need to figure out. But yeah, I don't think there is any proof that will work in different situations. But yeah, that is good to know that there is another alternative that is working out. And when you set this, when you set it to 50, is it working in with, let's say, only the random approach?
I didn't try fully random. I tried only 500 episodes.
Okay. 500 episodes of the blended version, like the exploration.
That's right, with epsilon decay of 0.999.
Right. So that is something we should bear in mind when we start solving problems. If we can tweak the reward structure so that the reward for reaching the goal state is a lot higher than the normal reward structure, does that give us a better policy more quickly?
Just curious though, so in this case, our state space is very small. So with the random approach, we can explore much of the space. And so having the final large reward, 50 for the reaching the goal works here. But if our state space is very large so that you cannot possibly randomly visit everything with a sufficient amount of counts, I don't think that approach would work.
Yeah, it generally doesn't work. That is where you bring in something like a model-based approach, where you introduce some information about what is more likely to work. right? So if you're driving a car, you might want to add additional constraint, additional knowledge about how the car operates, how the world operates, so you don't go around trying entirely random things, which will just waste your time and which will take a lot of time to converge.
And I think that's what I saw in what the answers were coming up with, was because for short paths, you could just wobble and hit the timeout of 20, the maximum 20 length path. And it was better to just do that than to risk going into the space where you might hit an opponent.
Okay, so that means there are two parameters to tweak, then the episode length and the reward, right? Did I understand it correctly?
Yeah, I think that there should be a larger penalty for timing out without hitting the end.
Okay. You're saying if you're timing out, then there should be a larger penalty. That makes sense. I think when we were discussing reward structures, I happened to share a formula that was being used in one of the papers, and they had one formula which basically had nothing but time in it, right? So one of the terms in the formula was time. So for how long are you able to sustain without reaching a terminal state? That was there. I'll reshare it in Slack again, but that was one of the terms. And that makes sense in our case as well. Adding additional uh, for reward or penalty, that depends on what you want to maximize. But in this case, because we want a shorter path, so I think we should be penalizing the amount of time that is being spent, right? Right. That was the idea, right?
Yeah, absolutely.
Cool. So it's good that we are coming up with these different things. We should start playing with this environment a little bit more, because we are pretty close to learning the basics, right? This is everything that we need to now start using something like q learning or SATSA. So we need to have at least some understanding. Of course, in many cases, in most cases, there is no underlying fundamental mathematics that will tell you that this thing needs to be tweaked, but at least we should have an intuitive feeling of how things change if you change the reward structure, if you change the episode length, if you change epsilon, all of these things. So what is the effect? Is the effect linear, non-linear? And that can only be possible if we play a little bit more with the environment, and then we try to debug it, try to print out the table, try to print the policy, and see what happens. So what we need to do at the moment is at least implement the constant alpha, or the other idea that we had of scaling up this reward function or this part without having to divide by the visit count. So if you can make sure that it doesn't go down drastically with the number of iterations, then we have a better shot of at finding a policy, because that comes from my experience playing with the environment, uh, and that is of course also like a standard trick that is used. So let's go back to the breakout rooms once again. Let's try to implement constant alpha, or if you have any idea of your own, try to implement that, and just make sure that this time we outperform this approach. So in this approach, we saw that we were sort of hitting saturation somewhere. Even with 3000 steps, we weren't a lot closer to the optimal policy. So the expectation is that this time when we try, even if we don't, if it doesn't work out with 1000 steps, if we try to increase the number of steps, then we should get closer and closer to the optimal policy. Okay, I'm opening the breakout rooms again. Am I audible over here?
Yeah. So Farhan, right now what we're doing is we're making an update per episode, but are we gonna also be doing it per step eventually?
Okay, rooms are closing in a minute, and then we will continue.
Hey, Farhan, can you right now hear me?
I can.
Okay. So it's basically I was unable to ask the question because I think it was because this audio in your side had issues. So like what my question actually was in the previous case, just rather than trying to do alpha times the return minus whatever the previous return location, if I basically do in the previous step, if I'm not going to just like divide these estimated returns which comes after the for loop by the visit count thing, I basically get the same optimized policy for the previous method
right.
as well as this one. So that is my
Okay, so you're saying
so in that case, basically, what advantage this adds, and why were we dividing by the visit count? So that raises some questions.
yeah, so we were dividing by the visit count because we wanted, whenever you take average, so the whole idea is that random perturbations, they will cancel out. So there will be noise, there will be signal, and hopefully the noise will be random in different episodes. So that cancels out when you take the average, right? It's good that we are getting the same returns if you just do away with the whole concept of dividing here. um, I'm not sure if this is which will always work, but for this case, if it is working, then that is also a possibility. We already have a list of things that different people have tried out, and it seems to be working. That's good to know. Uh, if I talk about the implementation of this specific change, which is constant alpha, so you can see that the current version, which is constant alpha, that looks like line number 19, right? So 2021 is what we had earlier, where we were adding the return. Now all we are doing is taking that return and then subtracting the current value and then multiplying it by alpha, and then adding it to estimated return table, right? So just multiplying the difference, which means if return is higher, right, if return was higher, then this value would be positive, and that means we want to increase our existing estimate in the table a little bit, right? Because the most recent episode is saying that you should get a higher return, so we want to increase the return. If the return is lower, then this value obviously will be negative, and then we want to slightly decrease the current estimate, but only slightly. That is why we multiply by alpha, right? If I run this with 1000 iterations, for 1000 iterations, uh, it will take a little while, and this is how the policy looks like. Again, it doesn't give you a lot of confidence, uh, but if you try to bump this up a little bit to 3000 steps, it will take a little over 30 seconds in my case, but let's see how different the results look. Okay, so finished in 20 seconds, and yep, in this case, this is pretty close to what this is actually what we were getting earlier too as well, right? So from starting from few of the closer states to the goal states, you get a good policy, but you are still not able to switch this loop over here. This has this is still stuck, and I have tried with different values. I think if you change it to 5,000, sorry, if you change it to 5,000, then it pretty much fixes our problem. We should be done soon. Yeah. Yep. Right. So if you look at 5,000 steps, we seem to have almost nailed it. It is still not an optimal policy for every starting state. If you look at this state, then it's going left, and then it is taking this detour, which is totally unnecessary. They should just have pointed down. So that is still not fixed, but you at least figured out a solution for the starting state. Now the question is whether we have tried a lot of variations, incremental improvements, and we aren't sure which ones are worth the extra complexity, or if the changes are at least worth making, right? This one in particular makes sense because, as I mentioned, the non-linear effect of the denominator, that is going to have an adverse effect on the learning. So there might be multiple ways of fixing it. This seems like a simple way, which is also similar to how you do it in deep learning. There are other suggestions. Other than this, there were suggestions about decreasing alpha. So someone suggested that if you set it to 0.01, 0.001, then it performs a lot better, seems to converge a lot faster, which can be a sensible thing to do because 0.1 might mean you are flipping things very quickly, changing values very quickly, right? That happens in deep learning as well, where you don't get a stable learning curve if the learning rate is very high. That is one thing that we need to experiment with. And then there are lots of other parameters. The episode length, do you want to penalize like we were doing with the reward structure in the beginning? If you remember, we were penalizing every movement. So if you penalize that, does that reward structure consistently outperform this reward structure where you're just uh, giving a reward of 0 every time? So all of those things. And also, what about the final reward? How large it should be compared to all the other rewards? So all of those things, they are hyperparameters. We need to think about it, but we also need to experiment and find out, because uh, again, like there is not a lot of sound theoretical basis to these things. So it will be based on empirical data. So experiment with it and find out. Just some of the things I mentioned right now. So there was one suggestion about offsetting the effect of the denominator by using, I think the suggestion was to use the sum of geometry series, which is 1 over 1 minus gamma. If someone can figure that out and have an alternative, that would be nice to see. Of course, we talked about the length and introducing something that penalizes you for the duration or time, an episode length, a smaller learning rate. So there are lots of things to play with. And then there was the question of whether this is online learning or offline learning, which we haven't discussed yet. So we will do that in the sessions to come. But what I expect from everyone is experimenting more, because we haven't done too much of experimentation, because obviously there's only so much possible in a shorter session. But whenever you can set aside some time, try to play with the different parameters, try to print out the values in the tables, and try to print out the policies. These are the two most effective things you can use to debug the algorithm. And you should have an intuitive sense of where the algorithm is going wrong to be able to find the right solution. Right? Because when we venture out into the territory where we are using deep learning to train something, then there are lots of things that can go wrong with the neural network itself, or with the parameters and hyperparameters of the reinforcement learning part of it. So if we have a gut feeling about what could be going wrong, it would be a lot easier to test things in isolation and find out the root cause instead of just trying all the random things and seeing which one works, which one don't. This is again because it's based on, at least in part, this is random exploration. So again, there are no guarantees. If you run it next time, then you might see an entirely different policy, maybe a lot worse, maybe a lot better. That is why when you start looking at a lot of benchmarks, for example, with OpenAI, the target, if you want to if you want to achieve a baseline, they will often have something like, if your reward, if your cumulative reward over 100 episodes is above this threshold, then you have solved this problem. And that is because no matter how much you train the algorithm, there will be some jitter, there will be variation. So if when they define the baselines, that is usually in terms of windows. So over a window of 100 episodes, if you can get, or 100 trials, in fact, if you over 100 trials or 10 trials or whatever, if you can get sustain a particular level of performance, then you have met the criteria, right? So where are we going from here? Of course, tomorrow we will implement a few different algorithms. We'll give them names. We will start with their textbook definitions, and they are going to look very similar to what we did today, maybe a small change here and there. So we will understand all those algorithms, and then we will see what variations there are of those algorithms, and then we will try to put together all the terminology that we should be familiar with at this point, right? So we have talked about different things. We have talked about states, agent, environment, action, rewards, returns, discounted returns, policies, uh, and a return table, rewards table, all of those things. But we want to now be able to refer to them using the right terminology, which is used in the industry and academia. So these are sort of the two goals. Uh, and between now and tomorrow, whenever you get time, please rerun a few variations, think of other solutions, other possibilities, research other solutions. There are so many things to solve. Can we converge faster? Because it's taking around 5,000, 10,000 steps. Can we cut it down significantly using any of the tweaks? And can we do that consistently? That is one of the major open problems. So let's do that little bit of experimentation. Let's again meet tomorrow and work on the algorithms. And then in the week after that, like I mentioned, we will be making one big change. So from being right now, we don't have any probability involved when you're taking action, which is very unlike the real world. So we will introduce that bit of probability to this environment, and that will sort of set us up to solve a wider gamut of problems from the different frameworks like OpenAI Gym or our own problems. Once we introduce that, uh, yes, we will be ready to take on many different types of problems. Uh, and we will also, tomorrow, we'll also just get introduced to our take home project, which is the OpenAI taxi problem. It's a discrete problem. It's pretty much like the foolsball problem. So it's just a matter of applying these techniques and then being able to debug and being able to get the right baselines. So thank you for joining today. I'll share the recordings again. I hope that you so far you have been able to follow everything that we have been doing. There has been and there have been a lot of incremental changes. I don't expect everyone to be able to absorb everything during the session, but if you're not able to understand a particular step, or if you think your understanding is still not deep enough, then please go back, run the code again, try to understand it. The solution to all the cells will already be there on the solutions branch. So if you want to look for that, that is also fine, but give it a try yourself first. If there are any questions, please ask now. Otherwise, we will wrap up and then we'll meet tomorrow.
Thank you.
Yeah.
See you tomorrow.
Thank you. So Chris is mentioning this. I think Hashim also mentioned the same thing, that when you reduce alpha down to I think 0.01 or something like that, it performs a lot better. Cool. I'm going to stop sharing the screen, and I think we'll just meet tomorrow then. Thank you so much.
Okay,
Bye-bye.
thank you.